All right. Good morning, everyone. Am I audible?
Yes, sir.
Good morning, sir. Yes, you're audible.
Good morning. Okay. All right. How many of you revised whatever we had done in our last lecture? Can I assume all of you, or none?
Sir, I read from William Green.
You read from William Green. Okay. Others?
Sir, I read from Woolbridge, sir.
Okay. No issue. चीजें समझ में आई. That's the
Sir,
most important aspect.
सर चीजें तो आई समझ में सर. उसमें एक चैप्टर मल्टीपल रिग्रेशन है, थर्ड चैप्टर से, तो वो किया मतलब. बट आपसे कनेक्ट हो नहीं पा रहा था, मतलब कि आप जो बता रहे थे वो शायद विलियम ग्रीन में था और उसमें मतलब काफी बेसिक था वोल्बेज में. तो बट मैं वहीं तक कर पाया था, तो मतलब वहीं तक मेरे को समझ में आया अच्छे से. अभी आगे तो नहीं करना ना उसमें?
नहीं.
ठीक है सर.
What would others? Avni, Mehir, Sharanya, Sayoni, Sarvesh. Don't compel me to pinpoint your name.
No, sir. I went through what you taught in class and
Okay.
a little.
Okay. So revise करके are you confident? Okay. So is there any issue with what we have covered till now?
No, sir.
Nothing
as such.
Okay, all right. So if you actually notice, when you read Woolridge or for that matter Damodar Gujarati textbook, what you notice is that we have covered multiple regression in just one go. So whenever you write or express these equations in matrix notation, जो हमने देखा था कि if you have more than one explanative variable in the model, that becomes an example of multiple linear regression model. So उसके लिए कोई अलग से चैप्टर पढ़ने की जरूरत नहीं है, and that's why matrices method helps you understand, helps you visualize these things even much better. So let me just start the recording and present my screen. Just give me a second. Okay, all right. Can you all see the screen?
Yes, sir.
Okay, all right. हाँ जी, तो हमने लास्ट क्लास तक क्या देखा था? That we derived the normal equation and we understood why precisely they are being called normal equations. So one geometric intuition that we had got was कि y जो actual y observation है, which is observed in the data, that is which is recorded as the dependent variable, that exactly lies outside the space spanned by the linear combination of the regressors or explanatory variables in the model. और OLS और जो principle of OLS ये बोलता है that you have to choose such value of these OLS estimators which are based on sample that takes the fitted values of regression as close as possible to the actual values of regression. And we know that the closest distance between 2 points in this Euclidean space can be thought as a perpendicular line. So we drop a perpendicular from the actual value to the fitted values in the plane spanned by the regressors, and that perpendicular is nothing but your error term. So principle क्या है OLS का? You have to choose, you have to select such values of B, those OLS estimators, which makes the residual sum of squares, that is sum of squares of the residuals. Residuals are what? Residuals are nothing but your error term of the sample. So I have to select such values of B which makes the residual sum of squares minimum. So, when we, and in matrix notation, I know that RSS, that is residual sum of squares, is nothing but I can get this by pre-multiplying this vector of residuals by its transpose. So this gives you E transpose E, which is your RSS. You have to minimize this RSS with respect to B. And the equations that we got was called normal equations, which was written as X transpose XB is equal to X transpose Y. And now you must notice, and I have not written this coefficient of B in expanded notation, but आपको ये चीज एक समझ में आनी चाहिए that I can write this B as X transpose X inverse X transpose Y. Precisely why? Because you cannot divide in matrices. So if I have to get rid of this X transpose X term from the left hand side expression, what I do is I pre-multiply this X transpose X by its inverse. So I know that A inverse A is nothing but identity. So X transpose X inverse multiplied by X transpose X is identity, which gives you B is equal to X transpose X inverse X transpose Y. और अगर आप actually notice करो ये जो B है, which is the OLS estimators or OLS coefficient, which are the estimates for the population parameters, it is based on the data matrix. You look at here term, this is X transpose X inverse. This is nothing but your data matrix. This is your X transpose Y. This is Y you collect as observation. X already you collect as your data. So B जो है आपका, that depends on the data. That depends on the observations that you have collected on the explanatory variables and the dependent variable. So ये बहुत ही obvious है that if you change these observations, if you change the sample, if you change those observations pertaining to the dependent variable and explanatory variables, your B is bound to change. And precisely this is the reason why we say that B itself is a random variable. And since B, why we are calling it as a random variable? Because it depends on the observations taken in the sample. तो एक रिसर्चर ने मान लो 50 ऑब्जर्वेशंस कलेक्ट किया X और Y पे, दूसरे ने 50 ऑब्जर्वेशन कलेक्ट किया पर सैंपल उसका डिफरेंट हो गया. So since B depends on the sample value, sample observations related to X and Y, B becomes, or B in turn is a random variable because it depends on the sample values. And the moment it's a random variable, you know that there's an element of probability attached to it. So we want to talk about the distribution of this B because it's a random variable. So I must have a distribution of B through which I can theorize, I can generalize about the population parameter. That's what the ultimate idea of econometrics is. So this B becomes a random variable characterized by a given probability distribution, and I know that two important parameters of any distribution function is mean and variance. So उसी तरह आप mean and variance B का भी निकालोगे. And now you should appreciate the reason why we assume normality of error terms is because B ultimately is a sum of, or is a linear combination of the error terms in the model. And one of the property of a normally distributed random variable is that the linear combination of that normally distributed random variable itself is normally distributed. So since your errors are assumed to be normally distributed with mean 0 and sigma square variance, your B will also be normally distributed with mean mu and जो भी variance of B आएगा. And now, since you know the mean and variance of this normally distributed random variable B, you can easily carry on with your hypothesis testing. That's what the crux of OLS is. Am I clear till here?
Yes, sir.
Okay, all right. Just give me a second. I need to change my laptop. Just give me. Okay, all right. Just one second.
Sir,
Yeah.
I didn't get the last part, mean and variance wala. Could you explain it again, please?
Which part you didn't get? Just explain me first.
The mean and variance wala part, like how does B and B, like how is B and B's, small b's variance related? Mean and variance related.
Come again. I didn't understand your question. I'm really sorry. Come again, please.
Like I mean how, like the small b's mean and variance part, like how is it related to e's mean and variance?
That's what we have not discussed as of yet. All I'm saying that the assumption of normality of error term is required so that you can have a normally distributed B, which we'll understand once we talk about beta to be a combination of Y and E. So for the time being, you understand that this beta can be written in the form of sum of error terms, and since error terms are normally distributed, one of the property of a normally distributed random variable is that sum of or linear combination of a normally distributed random variable itself is normally distributed. So we can write B as a function of E, which we'll see later in our later lectures. And since E is normally distributed, B also becomes normally distributed. And that's why we write B is normally distributed with mean mu. I don't know what this mean mu will be, and variance of B. Because this is how you write a normally distributed, and if X is a normally distributed random variable, you write X is normally distributed with whatever mean and variance. So that's what we have just talked about right now, and nothing else. I have not explained how do you write B as a linear combination of error terms, which is quite simple if you expand the normal equations, but I'll do that in lecture. Okay?
Okay, sir.
हाँ जी. Okay, all right. So अभी तक हमने क्या देखा? अभी तक हमने normal equations को derive करना देखा, and the derivation of normal equations are quite simple. And let me just write that normal equations over here. So x transpose xb, x transpose y. बहुत सारे बुक में हम नोटेशन देखोगे b के जगह बीटा हैट भी लिखते हैं. That's how they, in common terminology, they write the estimator part. But since I've used b, so I use this throughout. So इससे हमने एक important corollary देखा था last class में. That is, if you write, x transpose xb or y की जगह if I write xb plus e, क्या होगा? That this portion and this portion will cancel out. So what you get is x transpose e equal to 0. This is a very, very important, corollary that we derive from the normal equation. What generally it says is, you see, this is the observed values of x. So what it says that the observed values of x are uncorrelated with the residuals. That's why you have this, dot product of x and e to be 0. So what it implies that not a single observation on regressor, on each of the regressor, contain any information about the average or conditional average value of the residuals. What this says is that for every column of the data matrix, the correlation or each regressor has 0 sample correlation with the residuals. So it only talks about the correlation part. It does not mean that X is completely uncorrelated with the disturbance. And that's what we assume for the population part. We assume this. And this is for the population. But this, whenever I am discussing in terms of E, they all are for the sample counterparts. So sample counterpart में सिर्फ यही zero correlation between residuals and the observed values of X are identified or are defined by the normal equations. But again, this gives a very, very important conclusion कि अगर आपका regression model में एक constant term है, that is intercept term है, so what it definitely implies is that summation EI equals 0, which again implies that E bar is equal to 0. और हमने last class में देखा था that E bar can be exactly written as Y bar minus B1, X1 bar minus B2, X bar, and so on and so forth. So what it also tells you that the regression hyperplane, if I'm talking about more than one independent variable in the model, so regression hyperplane passes through the means of the observed values, that is X bar and Y bar. It's a very, very important corollary that we get from, provided we have an intercept term present in our linear regression model. And that's why when you have a model without a constant term, lot many interpretation changes as far as OLS estimators are concerned, which we'll discuss. But if our regression model includes a constant, then the sum of residual equals 0, which automatically means that the sample mean of the residuals is 0. And since sample means of residual is 0, this also implies that the regression hyperplane passes through the means of the observed values of x and y. और इससे एक और corollary क्या होता है कि जो predicted values of y है, predicted values of y are what? xb, which can also be written as y hat is equal to xb. So what it says is that the predicted values of y hat, is uncorrelated with the residuals. So what it means is that y transpose E equals 0, y hat transpose will be what? B transpose X transpose times E equals 0. अभी हमने just देखा X transpose E is equal to 0, which automatically means that this expression is also 0. So what it means is that the predicted values of y, which are based on the data matrix, which are based on the observations on the independent variables in the model, they are also uncorrelated with the residuals. This is a very, very important, conclusion as well. And then the final thing is that the mean of the predicted y's, that is mean of y hat, is equal to the mean of the observed y's. So these are some of the algebraic properties of the OLS estimators that we generate. And why are we able to obtain such algebraic properties is because of inclusion of a constant or intercept term in the regression model. Am I clear till here?
So can you explain the last part once again? Like after the predicted value of y is equal to xb, but इसके बाद जो
Yeah. You see, what did I write here is that predicted values of y hat is xb. Again, it's written in right form because it's an estimator of x beta. So what it says is that even these predicted values of y are uncorrelated with the sample residuals. So y hat transpose times E must be equal to 0 in that case. Y hat is what? xb ka transpose multiplied by E is equal to 0. B ka transpose, so this will become B transpose X transpose E equals 0. ये X transpose E हमने देखा अभी ऊपर. So this automatically means that y hat is also uncorrelated with the sample residuals. And then finally you have that the mean of the predicted y क्या है आपका ये y hat. So इसका जो mean है y hat का mean is equal to mean of observed values. If you remember this comes from the assumption of exogeneity of the independent variables, where you assume expected value of mu given x is equal to 0, and then we understood that this x beta is also the conditional mean of y given x, and this y hat is nothing but the estimated values, or you can say the mean of the predicted y, which we predict using the x in our model. Of the predicted values of y based on the data is also equal to the mean of the observed values of y. So these are certain algebraic properties of OLS estimators, and these properties will always hold true. But again, you must understand that all these properties require an inclusion of a constant term in the model. So you should be very careful not to infer anything from the residuals about the disturbances. जो हमने residuals के लिए observe किया है, this is not necessarily be true for the disturbances. So residuals are for the sample counterpart. disturbances are for the population. For example, you cannot infer that the sum of the disturbances is zero or that the mean of the disturbances is zero just because this is true for the residuals, because you have to understand that ultimately these residuals are based on the sample. So from residuals, we cannot generalize anything for the disturbances which are there in the population, because these residuals are based on the sample observations. But once you have a sample fixed, once you have an intercept term in the model, these properties, as you know, as far as OLS estimators are concerned, will always hold true. Now, this uncorrelation of observed values of x's with the error term is a very important property which makes possible for us to write the actual y as a sum of two distinct components. अब ये देखते हैं क्या है, what I'm saying, what do we mean by here? So what I'm saying here is, अभी हमने last class में देखा था इसका geometric interpretation, that you know, if this is x1, this is x2, this is the fitted values of y, let me call it as y hat, and let us say this is the actual y, this is your e, so actual y, and since e and y hat, abhi humne dekha that y hat transpose e is equal to 0, which means this vector consisting of the residuals, and this vector which consists of the estimated values or predicted values of y, the angle between them is 90 degree. So I can write y as sum of two distinct components given by y hat plus e. So I can write the actual observed or actual observations on y as sum of two distinct components precisely because there is zero covariance between the regressor and the residuals. So this zero covariance between the residuals and the regressors, it underlie one of the very important property which are called as decomposition of the sum of squares. So अगर आप actually देखो, इसको मैं actually समझ सकता हूँ ऐसे, that this is my e, this is my y hat, this is my y. So I can easily employ Pythagorean theorem here, and I can write y squared as y hat ka square plus e square. But this is not a scalar quantity, these are the vectors. So in matrices notation, how do we write them in terms of sum of squares? So what we do is, we pre-multiply both the side of the expression by its transpose. So left hand side expression becomes y transpose y. This can be written as y hat plus e transpose times y hat plus e. And now if you expand this, this will become y hat transpose times y hat plus y hat transpose times e plus, e transpose y hat plus e transpose e. Now if you actually notice, these two terms will be equal to 0 precisely because the estimated value of y or predicted value of y is uncorrelated with the residuals. So I can write this y transpose y exactly as y hat transpose y hat plus e transpose e. Now if you actually notice, this y hat transpose y is what? Y transpose y is what? This is the sum of squares of the actual y values. But generally we are not interested in sum of squares of actual y values. Instead, we are interested in analyzing the variation in y. and variation in y is nothing but,
So can you repeat?
yeah, ultimately we are interested in finding out the variation in y rather than sum of squares of the actual y. Variation in y क्या है? You must understand, since we are talking about sample, so मान लो एक particular x के लिए मैंने 10 values of y लिया, so sum of squares mainly क्या होगा? हर एक y का square कर दो and then sum them up. We are not interested in this aspect. What we are interested in, that depending on this value of x, how y is distributed around its central value or mean value. And that is called as variation. And when you divide variation by the degree of freedom, that becomes variance. So ultimately what I'm concerned about is, I'm concerned about this quantity. And this is called variation in y. That is how each values of y is distributed around this mean value of y. So if you just take the deviation from the sample mean and sum them up, they are called variation. And if I divide this by degree of freedom, let me call it a small sample, so n-1 से कर दूंगा, so this will become variance of y. This is the difference between variation and variance. So variation is the sum of squared deviations around the sample mean. That is variation. And when you divide variation by the degree of freedom, that becomes variance. So ultimately we are concerned about this aspect rather than this aspect. So what do we do then? That is, ultimately we are concerned about summation yi minus y bar ka whole square, and which can be easily written as n times y bar ka whole square. If you expand this a minus b ka whole square करके आपको यही term आएगा. You can just easily verify this. So ultimately what do I notice is that if in this expression I need this term n times y bar ka whole square, what do I do then? What do? I subtract n times y bar ka whole square from both the sides of the expression. And then I can easily write it as y transpose y minus of n y bar ka whole square can be written as y hat transpose y hat minus of n y bar ka whole square plus e transpose e.
So you're saying whole square. Sorry.
Come again?
You're saying whole square, but you're actually not doing whole square. So is it whole square or not?
I'm not doing whole square. Where?
You said whole square, but you are writing y y bar y minus n y bar square. You're saying whole square. Whole square.
No,
means
y bar ka square. I'm really sorry. It should be n times, because ultimately I'm subtracting this term.
Yes,
only.
I got it. Yeah, just confusion in like how you were saying it.
Acha. So I'm subtracting only this term n times y bar ka whole square. Sorry, y bar square, I should say. So this term here, y transpose y minus n times y bar ka square, is your total sum of squares. Now if you look at this term, y hat ka transpose, y hat is nothing but your xb. So y hat ka transpose can be written as b transpose xb minus of n times y bar ka square. This is called your explained sum of squares. And finally, this E transpose E is nothing but your residual sum of squares. And precisely this TSS is equal to ESS plus RSS. It is called as decomposition of sum of squares. तो व्हाट इंट्यूटिवली ये इक्वेशन, ये एक्सप्रेशन क्या बोलता है मुझे? ये बोलता है कि ये जो TSS है ये आपको टोटल वेरिएशन इन y बताता है अराउंड इट्स मीन वैल्यूज. Now, out of this total variation in y around its sample mean values, how much of that variation gets explained by the regressors that have been employed in the model? It is called as explained sum of squares. That is, इस y में जो भी वेरिएशन आपने नोटिस किया है उसका कितना प्रोपोर्शन ऑफ वेरिएशन जो आपने रिग्रेसर एज अ रिसर्चर आपने एज अ रिग्रेसर जो यूज किया अपने मॉडल में उसका कितना प्रोपोर्शन ऑफ वेरिएशन आपका रिग्रेसर एक्सप्लेन कर पाता है. If the explanative variables that you have included in the model best fit the population, then your R square of the model, that is the proportion of total variation explained by the regressor, is nothing but your R square. That should be very high. So a common, terminology में हम ये बोलते हैं कि a model with high R square is preferred over a model with low R square. Now, if you happen to be a graduate with not enough knowledge on econometrics, then you should understand this phrase with a caution. क्या ये हमेशा जरूरी है? So in that case, which we discuss later on, in that case, we must be able to understand that R square, which is your ESS upon TSS. So R square is based on a concept of sum of squares, and this sum of squares is based on the concept of the sample mean or the deviation of individual observations around the sample mean. And ये based in numerator में मेरा ESS, it means if I go on including the number of explanative variables in the model, it is bound to happen that my R square may or may not increase, but it will never decrease. And that's why it is said that R square is a non-decreasing.
So,
हाँ जी.
so you mentioned that it'll keep on increasing, but it may not decrease. Could you just repeat that point, sir?
Yeah. What I'm saying here is that, if I have a model which is written as beta naught plus beta 1 x1 plus EI, इसका एक R square होगा. Now, if you include another explanative variable x2, उसका R square, another explanative variable x3, उस model का R square. So what I'm saying here is that if you keep on including or adding additional explanative variables in the model, your R square may or may not increase, but it will never decrease. It means आपने जो भी additional explanative variable include किए हैं model में, that will have an impact on this ESS, explain sum of squares. So that additional explanative variable might or might not increase this ESS, but it will never decrease ESS. And that's why your R square is a non-decreasing function of explained sum of squares. And that's why you should always use this phrase with caution that किसी मॉडल का R square अगर ज्यादा है वो मॉडल better fit है. No. क्योंकि मान लो आप दो मॉडल को कंपेयर कर रहे हो, एक मॉडल में आपने 5 एक्सप्लेनेटिव वेरिएबल यूज किए, एक मॉडल में आपने 7 एक्सप्लेनेटिव वेरिएबल यूज किए. हो सकता है जो जिस एक्सप्लेनेटिव वेरिएबल में आपने 7 एक्सप्लेनेटिव वेरिएबल यूज किए, सॉरी मॉडल में, हो सकता है उसका R स्क्वायर लेट्स से 1% से ज्यादा है दूसरे वाले मॉडल से. Does it necessarily mean that the second model is better than the first model, where R square is less by 1%? As a student of econometrics, you should say or you should reserve your comments. Can you say it with full certainty? You should not. Because सबसे पहली चीज, since R square is a function of explained sum of squares, which again is a function of how many number of explanative variables are included in the model. So it will be crime, it will be erroneous on our part to compare two models which differ in the number of explanatory variables used in the model. And that's why there is another variable, or there is this another statistic which is used to compare two models which differ in the number of parameters used, and that statistic is called your adjusted R square. और एक और चीज याद रखिएगा that ultimately आप देखो आप कर क्या रहे हो. एज अ रिसर्चर आपने पॉपुलेशन का एक अजम्पशन लिया, उस पॉपुलेशन का एक रिप्रेजेंटेटिव फॉर्म में आपने सैंपल लिया. सो जो भी आपका सैंपल ऑब्जर्वेशन है, दैट इज योर लिमिट, दैट इज अ लिमिटेशन दैट यू फेस. सो सपोज आपके पास 50 ऑब्जर्वेशंस है, आपने एज्यूम किया एक लीनियर पॉपुलेशन रिग्रेशन फंक्शन, सो दैट्स व्हाई यू हैव अ लीनियर सैंपल रिग्रेशन फंक्शन, एंड लेट्स से आउट ऑफ 50 ऑब्जर्वेशन यू आर ओनली फ्री to use 50 observations. So suppose initially आपने अपने मॉडल में 3 एक्सप्लेनेटिव वेरिएबल यूज किए. So you must understand that first you have to estimate the parameters for those unknown population coefficient, that is 3 here, plus an additional constant term. So you have to first estimate those 4 unknown population parameters. So you lose 4 degrees of freedom over here. That is, out of 50 observations, you're only free to use now 46 observations. So you must understand that R square also imposes a significant penalty in the form of degrees of freedom in the sample. An unnecessary number of explanative
R
variables.
square or adjusted R square?
Yeah.
Sir, could you please repeat this part?
Haji, what I'm saying here is that R square imposes a significant penalty in the form of degrees of freedom in the model. क्योंकि आपके पास जितना नंबर ऑफ एक्सप्लेनेटिव वेरिएबल्स होगा, उतने ही ज्यादा पैरामीटर्स आपको एस्टिमेट करने होंगे और उतने ही ज्यादा डिग्री ऑफ फ्रीडम आपका कम होते जाएगा.
So doesn't that mean adjusted R square puts a penalty on the number of parameters instead of R square?
See, R square, why I'm using this penalty term is because you have to understand that R square तुम्हारे डिग्री ऑफ फ्रीडम को इम्पैक्ट करता है. That's what I mean. And degree of freedom means what? Since I know that R square is a non-decreasing function of ESS, and if as a researcher I keep on including the additional number of explanative variables in the model, उतना ही ज्यादा degree of freedom मेरा कम होते जाएगा. That's what I mean by this statement when I say that penalty on degree of freedom. Ultimately, adjusted R square इसी चीज को account में लेता है. That if you keep on adding additional and unnecessary explanative variables in the model, it has, or since it takes into account the degree of freedom in the equation, in its formula, in its statistic, that's why adjusted R square is a better measure to compare two models which differ in the number of explanatory variables in the model. So in that case, definitely adjusted R square imposes that penalty. But the statement in regard to R square was made here just to understand this, reasoning that inclusion of additional and unnecessary explanative variable in the model leads to decrease in the number of free sample observations researcher is able to use.
Sir,
Am I clear till here?
sir.
Hadi.
Sir, could you please repeat that adjusted R square part? Like, थोड़ा slow, sir.
Haji, what I'm saying here is that R square, since it's a non-decreasing function of the number of explanative variables in the model, so it would not be a better idea to compare two models which differ in the terms of number of explanative variables. So in order to compare such models which differ in the number of explanative variables, we use a statistic which is called as adjusted R square. अभी मैंने adjusted R square को define भी नहीं किया है. All I am saying is that R square को कंपेयर नहीं करना है जब भी आपको मॉडल दो तीन मॉडल जो भी दिखे जो डिफर करते हैं एक्सप्लेनेटिव वेरिएबल्स में या फंक्शनल फॉर्म्स में. इन सच टाइप ऑफ केसेस क्यों नहीं कंपेयर करना चाहिए? उसका रीजन है कि जो आर स्क्वायर है वो एक नॉन डिक्रीजिंग फंक्शन है एक्सप्लेनेटिव वेरिएबल्स का. सो हो सकता है कि अगर आपके एक्सप्लेनेटिव वेरिएबल कुछ भी ऐड ना करे आपके एक्सप्लेन सम ऑफ स्क्वायर्स में, बिकॉज अल्टीमेटली मेरा मोटिव क्या है? अल्टीमेटली मेरा मोटिव ये है कि y का जो वेरिएशन है अराउंड इट्स मीन वैल्यूज, उसमें significant proportion of that variation should be explained by the regressors that I have used in the model. And since R square is a non-decreasing function, तो एक रिसर्चर को इंसेंटिव मिल सकता है कि he can go on adding number of explanative variables in the model, even at the pretext of a very, very minuscule increase in the value of R square that he obtains. But is he right in doing so? Not necessarily. And that's where the concept of adjusted R square comes into picture, which we'll, discuss in a short while.
Sir, I have a question.
Haji.
Sir, even if we have one variable in the model, most of the times we observe that the R square and adjusted R square values are different, even though there is a single variable. So what is the possible reason for that? Because
the formula that R square adjusted R square uses is different.
But
in R square, in calculation of R square, we do not take into degrees of freedom into account.
Okay.
We do not divide these numerator and denominator by their degrees of freedom, respectively.
So the concept basically talks about how any insignificant or not very significant variable is contributing to the model. So the effect is taken out by adjusted R square, right?
Right.
So if there is only a single variable, should it not be the case that just because this formula thing that you're saying that it takes degree of freedom into consideration, wherein there would be only one degree of freedom lost, in the sense whatever would be the estimated value of x there.
But you're not getting the point that in the denominator you have TSS, uska degree of freedom is n-1. So let's say if you have 100 observations and you're calculating R square is simply ESS upon TSS, whereas adjusted R square will be 1 minus RSS upon degree of freedom upon TSS upon degree of freedom. The calculation is bound to be different.
So it should be a very minute difference, right?
Whatever difference it comes, but it has to be different. And you have to understand that when we move from one variable to more than one variable, what we get is this R square is called your coefficient of determination, or sometimes multiple determination. So adjusted R square takes into account the degree of freedom, because ultimately you understand these are sum of squares term or variation term or sum of squares term, sorry. So ultimately जब RSS upon degree of freedom n minus k कर तो ये बन जाता है variance. So the two terms are different. Again, TSS में जब मैं n-1 करूंगा, ये बन जाएगा variance of y. Whereas in R square it is only the variation of y. And that's the basic difference between R square and adjusted R squares. Is this clear?
Sir, my doubt is because you're saying just because it's losing a degree of freedom, that is why we observe a different value. But my concern is if there is a single variable, so it's that single variable is only trying to determine the effect on our independent variable, right?
Correct.
So because there is nothing else except for the disturbance term which is already existing in that particular set of data that we have, should it not be the case if it was not for formula, let me just put it this way, so would it be actually the same if there is a single variable?
No, it cannot be. Precisely
Then
because
I did not understand, sir.
precisely because R square is ESS upon TSS, and your adjusted R square takes care of this. And there's a difference between them. Your adjusted R square can be negative as well if you have more than one number of variables. And first of all, adjusted R square is an improvised, or you can say modified form of R square to take care of the degree of freedom which R square does not take into account. And that's why these two are concepts which are different from each other. So जब आप more than one variable में जाओगे, हो सकता है R square किसी का पॉजिटिव आ रहा हो, बट द नंबर ऑफ जितना भी आपने एक्सप्लेनेटिव वेरिएबल यूज किया है वो इफेक्टिव नहीं है एक्सप्लेन करने में. योर एडजस्टेड आर स्क्वायर माइट टर्न आउट टू बी नेगेटिव एज वेल. So it is just not on the basis of formula. It is also on the basis of how these formula or how these two statistics are calculated using the observations. Because in adjusted R square, we take into degree of freedom. Even when you have one number of explanative variables, it does not matter, because ultimately what you're doing is in denominator you're dividing TSS by a quantity. It's a number. So it has to be different. And whereas the point of degrees of freedom is concerned, that is in relation to when you have more than one number of variable. And let's say you are running two models where let's say in one model you are using only one variable, in the second model you are using three variables. Can I compare the R square of these two models? I cannot. So if I cannot compare the R square of these two models, what should I do? I should calculate adjusted R squares. And the model in which adjusted R square has a greater value, that model will be selected. That was the purpose of adjusted R square to begin with. Is that clear?
Yes, sir.
Because ये जो adjusted इसको इसीलिए बोलते हैं क्योंकि जो R square का वैल्यू है आपका, वो उसको एडजस्ट करता है with taking degrees of freedom into account. And degrees of freedom is that part which talks about how many number of observations are free at your disposal to be used. And ultimately it comes in this denominator and numerator. It's like F test. जो आगे पढ़ेंगे F ANOVA जो होता है. Ultimately ANOVA is called analysis of variances. Why do you say analysis of variances? Precisely because you have these sum of squares, they are divided by degree of freedom. So numerator divided by degree of freedom, denominator divided by degree of freedom. So ultimately F statistic is a ratio of variances. Whereas if you do not divide them by degree of freedom, then F ratio will be a ratio of variations. And this is the difference between R square and adjusted R square. So R square only compares or only is a measure of ratio of variation. Whereas adjusted R square is a ratio of variances. And that's why they're bound to be different. Am I clear? Chalega, everyone, do you understand why R square and adjusted R square? Oh, we have not talked about adjusted R square. I'll talk about it once I move ahead and discuss the selection of models between based on certain criteria.
Sir.
Haji.
Sir, in R square, like basically R square is not putting some penalty in terms of degree of freedom, right, sir?
Correct.
So, sir, how it's like not fitting to the purpose what we are like getting from the adjusted R square.
See,
Exact term how?
suppose आप रिसर्चर हो, आपने एक मॉडल डिसाइड किया, ठीक है, आपके हिसाब से दिस इज द बेस्ट फिट टू द डेटा बिकॉज यू गेट लेट्स से आर स्क्वायर इज 94%. There is another batchmate of yours. What he does is he includes an additional explanative variable and run the same model, and then he gets R squared to be 95%. Can you say that this model is better than this? Can you say with certainty?
No sir, but in first appearance we can say like यहाँ पे हम और भी मॉडल यूज करें तो
नहीं कर सकते. In the first appearance also you should not compare. And if you are saying that you will compare, then you are not getting the formula. You are not getting on which it is based. It is based on this ESS, and ESS is nothing but BX transpose XB. So ultimately what you are doing is your X here, in which you have 3 columns, here you have 4 columns. So ultimately your ESS changes. So you cannot compare. And that is what the purpose over here is. So R square only tells you कि जो भी आपका वेरिएशन y में है उसका एक certain proportion of variation gets explained by the regressions that you have used in the model. And rest, the proportion of variation which is not explained, that you attribute to the residual sum of squares. So you should never indulge in comparison of two models which differ in the number of explanatory variables on the basis of R square. चलेगा ये बात?
Yes sir, yes sir. Thank you sir.
Okay. Okay, is there any doubt before I proceed ahead?
Sir, one more thing.
हाँ जी बोलो.
Sir, if some researchers take the same model and with like 3 parameter है like, and say someone take with the again same model with different 3 parameter like with this same model kind of, तो sir R square जो होगा वो explain करेगा सही?
Come again.
Like sir, like
आपके मॉडल है, 2 मॉडल है, 3 आपने एक्सप्लेनेटरी वेरिएबल लिए हैं, राइट?
हाँ, दोनों में से
दोनों मॉडल में 3 एक्सप्लेनेटरी वेरिएबल्स है, पर एक्सप्लेनेटरी वेरिएबल जो दोनों मॉडल के वो अलग अलग है.
हाँ, लाइक सेम चीज के लाइक डिमांड के 5 वेरिएबल है. So I am taking 3 out of like 3 कोई भी और आप 3 कोई भी ले रहे हैं, then we are comparing model. ये ऐसा वर्क करेगा?
See, as long as the number of explanatory variables are same, you can, but again you have to use it with caution.
Yes, यही मैं पूछना चाहता.
हाँ जी, अगेन आपको सिर्फ ये ध्यान रखना है कि या तो फंक्शनल फॉर्म में डिफरेंट नहीं होने चाहिए एंड नंबर ऑफ एक्सप्लेनेटरी वेरिएबल्स जो मॉडल में यूज किया वो डिफरेंट नहीं होना चाहिए. Is that clear?
हाँ सही है. Thank you sir.
Okay. All right. I'll just take one more topic here, and then I'll ask you to solve the question. I'm sure that you'd have, अगर आपके पास undergrad में econometrics होगा, you have done this, but let us do it in matrices method, which is called as, I can write this whole equation that we have obtained in deviation form. So this OLS or population regression function or sample regression function can be exactly written in the form of deviation form. Deviation क्या? Deviation around its mean value. So एक तो मेरा तरीका है, I can write this as x beta plus I can write this as this, and एक मेरा, let me write it as y is equal to xb plus e. This is equation in deviation form where y is expressed as something like this. These x's are expressed as something like this. That is, you take each of those raw observations, you calculate the mean or representative value of all those observations, and you take each individual observations and take the difference from or take the deviation around its sample mean values for each of those vectors concerned. And that is called expression of, or expressing those equations in deviation form. Let us look at in very brief. So I can write my equation as, let me write it as, where your I goes from 1 till n. Now deviation form में लिखने के लिए क्या चाहिए मुझे y bar का एक term चाहिए, x1 bar का term, x2 bar का term, and so on till I need the term for xk bar. That is mean of these explanative variables. So what I do is, I average this equation over the sample observation. So I can write this as y bar is equal to b naught plus b1 x1 bar plus b2 x2 bar so on till bk xk bar plus e bar, which should be 0 because the average value of residual in the sample is 0, so I just simply write it like this. Call it as equation 1, call it as equation 2. If I subtract equation 1 from 2, what I get here is, I write yi minus y bar is equal to b naught minus b naught will go to 0, so I can write it as b1 x1 minus x1 bar plus b2 x2i minus x2 bar so on plus bk xki minus xk bar and plus ei, because ei minus 0 will be ei. And then the common terminology, the way we write in statistics here is that I express all the observations which are expressed in the form of deviations in the small letter. So yi minus y bar, I can write this as small yi is equal to b1 x1 I small xi, b2 x2i plus b3 x3i so on till bk xki. And simply I can write this as y bx plus e. This is equation in deviation form. However, you must understand that when you write or when you express this OLS in deviation form, there is no intersectum involved in the model. But any single day you can find out this intercept from this equation where you can write b naught as y bar minus b1 x1 bar minus b2 x2 bar so on till bk xk bar. So easily this interceptum is easily obtainable by using the earlier equation that you have. But whenever you express OLS in deviation form, that deviation form does not contain any interceptor. And one of the advantages of writing OLS in deviation form is that it reduces the amount of calculation to be done. Am I clear to this point? Yes. Am I clear till here, till all of you? चलेगा यहाँ तक?
Yes, sir.
Okay. Yes. All right. So what I'll do is, I'll stop here and I'll ask you to solve a question. Let me just present my screen. What 5Q you represent? Okay, all right. Can you see the screen? Can you all see the screen?
Yes, sir.
Yes, sir.
Can you all see the screen? Okay, all right.
Yes,
So,
sir.
the question is that this table, it gives you the real per capita income in rupees. So that is explained in terms of Y. Let me write it. This is my Y. One second.
Sir, you might want to go to that cell and right click and insert new column.
कहाँ पे? नहीं नहीं, I
Sir,
just want to edit this यार ये.
sir, वो जो three darkened tabs दिख रहे हैं आपको top पे, those are for the table.
ये ना?
Design layout सबसे right पे.
ये क्या?
सबसे right पे sir. Design layout pens. एकदम right पे darkened होंगे sir. Design और layout. Sir.
हाँ ये pens correct. Anyway, let me. So this per capita income is expressed as your dependent variable, that is your Y, and there are precisely two independent variables. One is your percentage of labor force in agriculture in India, and average years of schooling of those of population over 25 years of age. ये याद रखिएगा. So basically क्या है ये कि in the year 1985, 15 observations were collected on per capita income of certain individuals in rupees, and two explanative variables or two independent variables which are used in this model is the percentage of labor force employed in agriculture and average years of schooling of the population over 25 years of age. What you have to do is you have to find the least square regression equation of y on x1 and x2, and the results that you get, you have to interpret them. Is that question clear? You have to find the least square regression of y on x1 and x2. So this is your x1, this is your x2, this is your y. These are the number of observations, 15 number of observations are there. So this table gives you the real per capita income in rupees, which is your Y, percentage of labor force in agriculture, your X1, and average years of schooling of the population over 25 years of age as X2. You have to find first the least square regression equation of Y on X1 and X2, that is you have to estimate those beta naught, beta 1, beta 2. And then you have to interpret those results. Is that clear, everyone?
Yes, sir.
Preferable, don't do it manually, either do it on Excel because the calculation will be much easier, and just write or just try to solve this equation using the normal equations the way we have derived them. So the time given to you is exactly half an hour, so I'll start discussing on this problem exactly at 11. So if there's anything that you need to ask in the between, I'm here. You can either write a text or you can simply unmute yourself and ask. So time is half an hour. Please try this.
सर
या बोलो शुभम।
सर थोड़ा बता दो प्रोसीड कैसे करना है, मतलब समझ में नहीं आ रहा है कि लाइक स्टार्ट कैसे करें। इक्वेशंस तो मेरे को समझ में आ रहा है कि क्या करना है, बट सर थोड़ा सा आप एक दो
सबसे पहले
स्टेप्स बता
नॉर्मल
दो सर।
इक्वेशन लिखो। सबसे
ठीक है
पहले
सर।
नॉर्मल इक्वेशन क्या है आपका, एक्स ट्रांसपोज एक्स बी इज इक्वल टू एक्स ट्रांसपोज वाई, राइट
सर
है ना। अब आपके पास
यस
एक्स तो
यस सर।
दिया हुआ है, एक्स इज
यस
योर
सर
एक्स
एक्स
वन
दे
एक्स
रखा
टू,
है। हाँ हाँ सर ठीक है।
ठीक है। तो एक्स का आप ट्रांसपोज
यस सर।
निकालिए, या तो आप उसको डिवीजन फॉर्म में भी सॉल्व कर सकते हैं। डिवीजन फॉर्म में क्या करना है, सिंपल आपको टेबल लिखिए y x1 x2, फिर y का डिवीजन लिखिए, x1 का डिवीजन x2 का डिवीजन, कैलकुलेट दोस टर्म्स, x1y x2y x1 x2 x1 स्क्वायर x2 स्क्वायर, यही तो चाहिए,
ओके सर थैंक यू, करता
है
हूँ।
ना। आप एक्सेल पे करो, मैनुअली डू नॉट कैलकुलेट देम, इट विल बी इजी।
सर
हाँ या बोल।
हाँ सर, ये सब करने से अच्छा डायरेक्टली एक्सेल में डाल के डेटा एनालिसिस टैब से ऐड इन किया तो नहीं चलेगा?
वो फिर शॉर्टकट हो जाएगा सर्वेश,
हाँ ठीक है सर,
है ना।
क्योंकि सर आउटपुट सेम ही आएगा।
Obviously, because Excel does all the things for you, na OLS, but I don't want that.
ओके ओके सर।
हाँ जी।
Yes, sir.
Okay. Anyone of you got the answer?
So the values,
Haji?
sir, I got B1 is equal to 6.20.
Okay.
B2 is a negative number.
Okay.
It is 0.376.
Okay.
B3 is 0.452.
Okay. Fair enough. And interpretation part, Setu?
So basically, the effect of labor force in agriculture has a negative effect on the real per capita income.
Correct.
Um,
Okay, no issue. Thank you so much. And answers are correct. What about others?
Same values, sir.
Okay, okay. Others apart from Neil and Setu? Now tell me how many of you did not at least, get an idea how to go about the process. I start from there.
Sir, I didn't.
Okay, no issue. ठीक है अब इस पहले प्रॉब्लम को देख लेते हैं देन Hi, I'm really sorry there was internet connectivity issue. Can you all hear me now?
Yes, sir.
Yes, sir. We can hear you.
Okay. So let me just start solving the problem. Let me just present my screen 1 second. Yeah. So you see, this is a question that has been given to me. First thing that I notice here is, without any thinking, सबसे पहला चीज आप क्या करते हो? You just write your normal equations. नॉर्मल इक्वेशन क्या है मेरा? नॉर्मल इक्वेशन है x ट्रांसपोज x b is equal to x transpose y. Now this is my y, per capita income is my y, x1 x2 is my x, that is the data matrix. Since we assume that our population regression function contains an intercept term, so the kind of PRF that I have as per the question is, I can write that as y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus error term. And we already know the terms or the calculations that we require as far as the normal equations are concerned. तो नॉर्मल इक्वेशन के लिए मुझे क्या क्या चाहिए? मुझे x ट्रांसपोज x का एक टर्म चाहिए और मुझे एक टर्म चाहिए x ट्रांसपोज y का. It means if I get these two terms, I'll be able to solve the corresponding vector for b0, b1 and b2. वो कैसे देखते हैं? Let us see. Just give me a second. Guys, the internet is really bad today. Sorry. Whiteboard is not. Just give me some seconds, guys. Yeah. Yeah. So I know my normal equation. I know my normal equations is written as x transpose x beta, b is equal to x transpose y. अब मेरा जो x है, x क्या है मेरे पास? मेरे पास 15 ऑब्जर्वेशन है. जो फर्स्ट कॉलम होगा that will contain 15 ones. Then I have 9, 10, 8, 7, 10, 4, 5, 5, 6, 8, 7, 4, 9, 5, 8. This is my x1. And my x2 is 8, 13, 11, 10, 12, 16, 10, 10, 12, 14, 12, 16, 14, 10 and 12. So this is my data matrix X. So the dimension of this data matrix is 15 by 3. So जब आप इसका X transpose करोगे, that will become 3 by 15. So 15, this is number of column in X transpose, number of row in X. सो जो x ट्रांसपोज x का जो डायमेंशन आएगा दैट विल बी 3/3. सबसे पहला चीज जो ये देखना है. अब इफ यू नोटिस द x ट्रांसपोज x टर्म विल लुक लाइक, it will look like n summation x1 summation x2, और since ये सिमेट्रिक है x ट्रांसपोज x, तो आपका यहां पे भी summation x1 summation x2. This will become summation x1 square, this will become summation x1 x2. सिमेट्रिक है तो ये भी summation x2 x1 सेम ही होगा. So this is the term that I get for x transpose x. अब रही बात मेरे पास x transpose y की. So ये x transpose is a term which is 3/15. y क्या है आपके पास? आपके पास 15 number of observations on the dependent variable, so it is 15/1. So इसका जो multiplication होगा x transpose y, that will have a dimension 3/1. So सबसे पहला जो होगा summation y, second will be summation x1 y, third will be summation x2 y. And I can easily write it as n summation x1, summation x2, summation x1, summation x2, summation x1 square multiplied by b0, b1, b2 is equal to summation y, summation x1 y, summation x2 y. And then these are the observations, that these are the variables or these are the numbers that are given to you. You know n is 15, you know summation x1, you can calculate, sum all the x1, you know summation x2, you know summation x1 square, you know this term, you know this term. So all things are known to you. This is not known to you, but this is known to you again. अब इसको हम सॉल्व कैसे करते हैं? सॉल्व हम इसको बीटा नॉट, बीटा 1, बीटा 2, आई कैन इजीली राइट इट एज n summation x1 summation x2 summation x1 summation x2, ये term inverse of this multiplied by, now on Excel you can easily find the inverse of this matrix. You can you have these calculation, you find the multiplication of this inverse matrix with this, you will get the vector b0 beta 1 beta 2. That's why I said do not do it manually, you can easily do it on Excel. ये तो एक तरीका हो गया. सेकेंड तरीका क्या हो सकता है? सिंस आई नो माई PRF इज बीटा नॉट प्लस बीटा 1 x1 i प्लस बीटा 2 x2 i प्लस ei, I can express this in deviation form. So deviation form में कैसे लिखूंगा मैं? स्मॉल yi बीटा 1 स्मॉल x1 i प्लस बीटा 2 स्मॉल x2 i प्लस ei. तो जो नॉर्मल इक्वेशन होगा डिविएशन फॉर्म में, बहुत ही सिंपल एनालॉजी लगना है इसमें. मेरा रॉ फॉर्म में क्या था? x ट्रांसपोज x. So this was my raw values of x transpose x. अब डिविएशन फॉर्म में मैंने क्या किया है? Deviation form में I have taken each of the variable, calculated its mean value, took the difference of each individual observation around its mean value. That is my deviation form. So अब ये देखो जो पहला रो और पहला कॉलम है इस x transpose x का, that will go to 0 because this n minus n will be 0. Summation x1, this term will become x1 minus x1 का bar. And you know that sum of deviations of observations around its mean value is 0. So this term will be 0. Similarly, this term will also be 0. So the deviation form में आपके पास बचेगा ये matrix x transpose x का, that will be summation now small x1 square. Small x1 is what? x1 minus x bar का whole square. Similarly, here it will be summation x2 square, small x2 square. Here it will be, sorry, x2 x1. Here again it will be x2 x1 and here it will be x2 square multiplied by b0 तो होगा नहीं क्योंकि there is no intercept term in deviation form, so it will be b1 b2. And similarly x transpose y का जो term होगा summation y will go to 0. So the term that will be left will be here is summation small x1 y summation small x2 y. You can easily do this calculation again and find out the value B0, beta 1, beta 2. Is this clear to all of you?
Yes, sir.
Is this clear to you, Ayushi? How do we go ahead with this?
So could you repeat the deviation part again?
हाँ जी, डिविएशन पार्ट में मैंने क्या किया है? सिंपल डिविएशन पार्ट क्या है? Explaining or writing each of the variable, taking the deviation of each variable around its mean value. तो ये जो x transpose x है, this x transpose x is for the raw x. अब मैं इसको deviation form में बदल रहा हूं. It means each column को मैं for each column I am expressing it in terms of deviation. So ये सारा 1 1 1 1 1 है. So 1 minus 1 1 minus 1 1 minus 1, each term will be 0. So this first term will be 0 in the deviation form. This will become summation x1 minus x bar, x1 bar. Let me write it as xi1. So पहला observation of x1 minus its mean, second observation on x1 minus its mean. इस तरह से 15th observation का मैंने सब कुछ sum कर दिया है. And you know there is a property of arithmetic mean of observation is that if you sum the observations which are taken as deviations around its mean values, the summation of such term will go to 0. That is, summation x1 minus x bar has to go to 0. So this term will be 0. This term automatically will be 0. So the first row, first column will go out of your x transpose x. Now look at this term, summation x1 square. But this is I do not need. I need x1 minus x bar. That is xi1 minus x1 bar ka whole. So I need this term. So this I have written in form of small letters because when you express deviation form, you write in small letters. So summation big x1 square becomes summation small x1 square. Here I have summation x1 x2. This summation x2 x1 becomes summation x2i minus x2 bar multiplied by summation x1i minus x1 bar. So that's why it is in a summation x1 x2. Similarly, this term is symmetric, so this will be the same. And summation x2 square is summation x2i minus x2 bar ka whole square. So this is the term. Similarly, जो आपका x transpose y raw में होता है, उसका first term होता है summation y. If I write it as summation yi minus y bar, this term will be 0. So that's why I do not have any term. Here it will be summation x small x1 y, summation small x2 y. Now, if you actually expand this normal equation that you have got, you can easily write your beta 1 as summation x1 y multiplied by summation x2 square. You can apply Kramer's rule over here. Minus of summation x2y minus of summation x1 x2 divided by summation x1 ka whole square summation x2 square minus of summation x1 x2 whole square. All these terms are given to you. You simply have to put them here and calculate. Similarly, beta to b2 को भी आप लिख सकते हो Kramer's rule के through, and you can easily solve that. Now, once you solve this, what you get is your b1 comes as roughly equal to minus 0.38. Your b2 comes at approximately equal to 0.45, and your b0 is approximately equal to 6.26. Sorry. So how do I represent my OLS regression equation of y on x1 and x2? I write it as yi hat, because this is the estimated y, is equal to 6.26 minus of 0.38 x1i, or let me add xi1, plus of 0.45 xi2. So this is my estimated population regression function. How do I interpret this? As a researcher, you know that when an economy is heavily, where the population is heavily occupied, or they find their occupation in agriculture and its allied activities, the per capita income of that nation is bound to be low. So, as a researcher, you expect an inverse relationship existing between the proportion of labor force engaged in agriculture, or percentage of labor force engaged in agriculture, with that of per capita income. And this is what this sign, which is attached to this coefficient, tells you. That there is an inverse relationship between y and x1. Y here is per capita income, x1 here is percentage of people employed in agriculture. And the second explanative variable, which here in this case is average years of schooling of the population over 25 years. So you expect a positive relationship existing between per capita income of a nation and average years of schooling that nation has. And that's why you have a positive coefficient, a positive sign attached with the coefficient of x2. Now, how do I interpret this? This estimated ONS regression equation, it indicates that the level of real per capita income that is given by y is inversely related to the percentage of labor force in agriculture x1, but positively related to the years of schooling of the population over 25 years of age. Specifically, if I increase the percentage of population employed in agriculture by 1 percentage point, what it means is that on an average, this is where many people, interpret it wrong. Ultimately, this estimated regression coefficient is conditional average. If you remember, if you recollect from our earlier discussions on assumptions part. So basically this yi hat is what? Expected value of yi given this x. So that's why this is an average value of y. So what it says is, if you increase the percentage of labor force employed in agriculture by 1 percentage point on an average, there will be a decrease in per capita income of 380 rupees, because this is explained in percentage point and this is in raw form. That's why you multiply it by 100. So an increase in 1 percentage point of labor employed in agriculture will lead to decrease in per capita income of India by 380 rupees while keeping this x2 constant. This is how you interpret a regression equation. Keeping this x2 constant, if you increase, or for that matter, if I decrease the employment of labor force in agriculture by 1 percentage point, there will be an increase in real per capita income of India by rupees 380. Why I'm multiplying by 100 is because this coefficient is 0.38 and here x1 is increasing by 1 percentage point. This is in raw form. So in order to convert this, I multiply this by 100. Similarly, if this, what does beta 2 represent over here? If there is an increase of 1 year of schooling for the population over 25 years of age, on an average, there will be an increase of 450 rupees in per capita income of India while holding x1 constant. And then intercept term simply says that it has got no economic meaning attached to it. What it simply says is that if both x1 and x2 are 0, the real per capita income of nation will be 6.26 rupees, which does not hold any economic importance. In the first place, it also seems to be unrealistic in nature. So I'll stop here. In the next class, I'll talk about mean and variances of these OLS estimators, because ultimately we have just discussed that since this B depends on the sample observations, if you change the sample observations, your B is bound to change. And that's why B becomes a random variable. Since it's a random variable, there's an element of probability attached to it. So that's why it is characterized by a probability distribution function. Every distribution function is characterized by or parameterized by some important parameters. The two main important parameters of any distribution is given by mean and variance. And that's why we'll talk about the sampling distribution properties or sampling distribution of these OLS estimators in our next class. Now, mind you, these things, the calculation that we have done in today's lecture, this can easily be done on Excel. You simply go on the data analysis tab and there you have the simple regression. You just click it and your entire output comes. I know you know it, but the purpose behind asking you to solve this exercise was exactly to understand how software, in this case Excel, is actually calculating all this. So that's why whenever there is a problem, you ultimately are aware that where that problem would have come from. And then finally, interpretation of output is equally important. One thing which we'll discuss in our next lecture is also that when you have more than one variable in the model, it is called as multiple linear regression model, and the coefficient or those OLS estimators that are attached to each of these as coefficients, they are also called as partial regression coefficients. And the reason being, अभी हमने just देखा कि अगर मुझे B1 को explain करना है, which is the coefficient attached with the explanative variable x1. So in order to interpret B1, I keep the effect or influence of x2 as constant. And that's why it becomes partial in nature. So B1 explains the impact of change in x1 on y, keeping x2 constant. Similarly, B2 explains impact of changing x2 on y, keeping x1 constant. And again, please do not forget that ultimately this y hat is conditional observation, or sorry, conditional average. So you always interpret that whenever there is some change in x, on an average, how y is changing, this is how you interpret our OLS, or sorry, regression equation. So I stop here. I have an institute meeting to attend at 11:30, so that's why I'm not able to take it forward. In the next class, that is tomorrow, I'll start with talking about sampling distribution of these OLS estimators. And once we are done with sampling distribution of OLS estimators, we move to hypothesis testing as far as regression are concerned, and then we move to violation of assumptions of CLRM. That's where we discuss how do we exactly remedy, or what are the measures that we employ whenever we face it, whenever we have any violation of assumptions like homoscedasticity violate हो गया है, autocorrelation violate हो गया है, appropriate functional form नहीं है. So बहुत सारे combinedly they all are called as specification testing. So after we discuss the hypothesis testing, we move to specification testing, and that's where we devote certain time, and then we move to understand time series and simultaneous equation. So I'll stop here. Again, request whatever we have done today, please revise it. Ideally, I'll not give you an exam to calculate such type of numericals by hand. So these have to be calculated on Excel. if at all I ask them in exam. And once we are done with, once we are done till at least hypothesis testing part, that's where I'll give you certain exercises to be solved, which are at the back end of Woolrich, mentioned as chapter end exercises, and that to computer exercises. So you get enough practice on solving these problems on computers, and that's where you actually can start simulating your own data and then calculating these OLS coefficients. So I'll stop here. Next class, that is tomorrow, 9:30. I'll start from this point onward. I'll discuss a bit about equation and deviation form as well. Then I move to mean and variance of B and hypothesis testing respectively. So,
sir, do we have holiday tomorrow?
I don't know. Do we have holiday? But I'll take my lecture here because I might not be able to take lectures in coming week. So I'll finish at least some more portion. I'll take my lecture. Okay then. I'm really sorry. I'll not be able to take your questions today. You can easily ask the questions related to today's lecture tomorrow in tomorrow's lecture. So thank you so much for being in the class, and stay safe, and see you in the next class. Tomorrow.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.